All right, yeah, so before I actually begin the subject of my talk, I just want to make a couple of prefatory statements. First of all, about the question Randy asked, as far as record warm years, 11 of the last 12 years were among the 12 warmest years on record, that is, since thermometer records began in the late 1800s. So that's a major warning sign. And as far as the whole issue, I feel it's my duty as an actual climate scientist to address this. The issue that we don't have to take global warming seriously for another 80 years or so. I mean, that's, to be generous, that's pretty outlandish. And to be blunt, that's irresponsible and even denialist, in my opinion. There's mountains of evidence to contradict that. But if you want, you can convince yourself by simply doing one thing, and that is just look at the Summary for Policymakers report of the Working Group 2, the fourth assessment report of the IPCC that came out just earlier this spring. And in that, you'll see that they looked at about 29,000 observational data sets. Forget about models. This is historical observations, empirical data that span from 1970 to 2004. And what they found among those 29,000 data sets that they looked at is about 90% of them agree with the expectations of anthropogenic global warming. So this idea that that the impacts are still decades away is just total folly. There's again that alone contradicts that. We're already seeing the impacts. If you look at there's a nice table in that same Summary for Policymakers from Working Group 2 that shows a gradient of temperature along with expected impacts for each temperature range. And so they extrapolate this, the historical observations they made, historical analyses of the empirical observations that to say that if we go into the 2 to 3 degree range above today's temperature, then one of the impacts we can expect is up to 30% extinction of the world's species. So we're already seeing the impacts, and the point is, if we don't do something about it very soon, they're just going to get worse and spiral out of our control. For better or worse, the climate's in our control right now. But we might very well be passing tipping points as we speak. For instance, in the Arctic sea ice, the fabled, some of you might have heard about this, the legendary Northwest Passage opened up for this Arctic sea ice hit a record low this past September. So this is kind of breaking news, but and what they found was that it's about 20% lower than the previous record, which was just 2 years ago, 2005. Compared to the data, the record for which we have satellite data is from 1979 to the present. This was a record low this past September, and in fact it was so low that the spatial extent of the sea ice in the Arctic that this Northwest Passage, which is the waterway connecting the Atlantic with the Pacific, but north of Canada, so through the Canadian Arctic archipelago, that was open for the first time in known human history. So that's one sign that we might have already passed a tipping point. There are tipping points for lots of different components in the climate system, of course. For instance, the ice sheets presumably and hopefully we haven't quite reached the tipping point for them yet, but it seems that we've reached the tipping point for the Arctic sea ice at least. Okay, so on to the subject of the talk. First I wanted to go into what our paper is attempting to do and what it's not attempting to do, since there seem to be some misconceptions about that in the Pico blogosphere from the cursory reading I've done. So first of all, fundamentally we just wanted to develop emissions trajectories that explicitly, as Randy mentioned, incorporate what we consider to be plausible peaks in fossil fuel emissions. That is, explicitly incorporate limitations of resources that contribute to atmospheric CO2 increase, with a specific focus on very general and deliberately simplistic mitigation scenarios that keep atmospheric CO2 below what we consider, and Jim has argued this in other papers of Jim Hansen, in other papers of his, that the dangerous level of CO2, the level of CO2 that constitutes what's called dangerous anthropogenic interference under the UN Framework Convention on Climate Change, which, by the way, our government ratified under the Bush Senior administration in '92. Although it doesn't quantify what dangerous anthropogenic interference is. And that was deliberate because it simply wasn't known. It's still not known with any type of precision, but we've argued before that that a reasonable limit should be 450 parts per million CO2. That is about 70 parts per million above the current level. And ultimately, our hope is just to guide climate change mitigation policies using these, what we consider to be plausible mitigation scenarios. So let me just give some paleoclimate context. I was pleasantly surprised to see this morning, not just anyone at this conference, but a representative from a multinational corporation, the guy from Toyota, present the same curve of CO2 over time. So that at least one person knows, in one multinational knows what's going on, at least appreciates the proper historical context. And that context is shown here in terms of both CO2, atmospheric concentrations of CO2 and methane, as recorded in the Vostok ice core in Antarctica, which is an extremely high resolution, in fact, the best record we have for these two gases. And even though they're at near the South Pole, they are considered to be global, they represent the global concentrations simply because CO2 and methane are what we call well-mixed gases. But anyway, what this shows is that over 400,000 years, that is about 4 glacial interglacial cycles, CO2 has never gotten above about 300 parts per million, with the most immediate background pre-industrial level being about 280 parts per million. So we can see on the right-hand side is, notice that the time axis is slightly shifted there. So I think the Toyota guy showed it just on the same time scale. And if I did that, it would just be like he showed, which, namely a straight line going upwards. I'm talking about the CO2 trajectory since the industrial era. And it shows a clear exponential increase of about 100 ppm over the last couple hundred years. And the main point to take away from that is that that rate of change and that magnitude of change is unprecedented in definitely for the last 650,000 years, which is what this record has been, the published record has been extended to. And the unpublished record, they say, is 890,000 years, but we're still waiting for that to be published. But the point is, it's unprecedented in most likely millions of years, that is, when the glacial interglacial cycling began. And this is now basically indisputable. There's various lines of smoking gun type evidence to show both of these statements. Okay. So this, again, I could talk about this slide also for the entire time of my talk, but this shows a different aspect of paleoclimate over the same time period, the last 420,000 years for glacial interglacial cycles. This is sea level change versus temperature, global temperature. Also as recorded, the global temperature as recorded in isotopes measured from the ice cores, and global sea level rise as recorded in other paleoclimate data. Not from the ice cores. But what this shows basically is that if temperature is kept below, if global average temperature is kept below about 1 degree Celsius, what it is today, then sea level probably, well, we know it didn't rise above 5 to 6 meters when it was within that range. And therefore we think that keeping it below, keeping future change below 1 degree Celsius from the present should also cap sea level rise at around that amount, with much of the contribution coming from disintegration of West Antarctic and Greenland ice sheets. However, if we go more than that, about 2 to 3 degrees Celsius higher than the present, then that period, that temperature regime isn't represented in the paleoclimate record, except we have to go back about 2 to 3 million years. And at that time, this is an epoch called the mid-Pliocene. Equilibrium sea level was about 15 to 35 meters higher than it is today. That's about 100 feet higher than it is today globally. So again, the goal is simply to keep, the temperature goal is to keep 21st century temperature rise below 1 degree Celsius, what it is today. Okay, so that's what we are, that's sort of what our goals and motivation are. What we're not attempting to do is develop predictive scenarios. As some people have asked me, they think we're trying to pinpoint timing of peaks, and that's simply not the case. And we're also not trying to resolve the debate about the magnitudes of the reserves for each of the fossil fuels. The focus of the title of my talk in the paper was chosen very deliberately. The focus is strictly on the physical implications for climate, using a range of reserve estimates from commonly cited sources. And again, We're not pinpointing the timing or anything, so, and we're also not endorsing any particular set of reserve estimates or peak estimates for that matter. We're just looking at ranges that other people have developed more or less and seeing what they imply for CO2 concentrations and therefore climate. We're also not trying to debunk the so-called benchmark scenarios, the IPCC scenarios that came out that Randy briefly talked about in 2000 in this special report on emission scenarios. Those scenarios, actually there are hundreds of scenarios out there, of which 40 were distilled and put into this SRES report. And among those, there are actually 6 what are called illustrative or marker scenarios. And I'll show those later, how ours compare with those. And those are the scenarios that are used, the so-called benchmark scenarios in standard climate modeling studies. So when you see climate model projections, they almost always use one of these 6 illustrative scenarios. And you know, if you ask most climate scientists, they don't even know what goes into these scenarios. They just take them, they don't really critically assess them. They're just interested in the range of possibilities. They're not necessarily interested in what is probabilistic scenarios and so forth. And so along those lines, we're also not trying to develop probabilistic scenarios simply because we want to minimize our socioeconomic assumptions. Obviously, there's huge uncertainties involved with that, and therefore we took ultimately a deliberately broad and simplistic approach. But as I'll mention, I think there are certain general principles that we can glean from looking at these ranges of plausible estimates. Okay, so some definitions, I'll just go over these briefly. Proven reserves, supplies that are, and these are again, we didn't make up these definitions, these are what we consider to be standard ones, mostly from the EIA. Proven reserves, supplies that are known to exist with high certainty, relatively high certainty, but their magnitudes are obviously hotly debated, as we saw in this conference, and as many people argue. So among proven reserves, conventional reserves we consider to be usable under current or near-term socioeconomic and environmental conditions. Unconventional reserves are those that exist in a different physical phase. For instance, methane hydrates, which is a different, it's a solid phase, arguably, of methane. Although the methane is still gas, it's encapsulated in water ice. And those unconventional reserves are not yet, anyway, as feasible from either an energetic standpoint or an economic standpoint. Reserve growth term is, again, straight from the EIA, likely additions to reserves. Assuming current and near-term technology. Again, the magnitudes vary widely. I'm sure a lot of people here think that this term is actually 0. And except as noted, finally, the term peak, as we use it, generally refers to the Hubbert type peak. That is just the midpoint of the total resource base, historical plus projected reserve estimates for each fuel type. And oil isn't the only fossil fuel we looked at. We took a sort of general approach and applied the peak concept to coal and natural gas as well. And we felt justified in doing this because of what's shown here in these graphs, and also because of the fact that the mineral geologists realized actually decades before Hubbert that the mineral extraction also followed a similar pattern of rapid growth followed by a peak in the rapid growth in the extraction rate, followed by a peak in the extraction rate, followed by a decline in the extraction rate that was more or less symmetrical to the growth rate, the growth in the extraction rate. So we see that here for the other 2 fuels. In the graph on the left, it's statewide production of anthracite coal in Pennsylvania, covering a span of just over a century. And on the right is statewide production of natural gas from Louisiana. These are both from published sources. The second one is from the Department of Natural Resources, Louisiana. So you can see that at least in these 2 cases, coal and natural gas on a multiple site integrated level follow the Hubbert type curve. Okay, so that said, what are the assumptions that we made for resource supplies? They're shown here in this bar graph are 3 different columns. The purple estimates are the historical emissions data, which we took from the CDAC. Maybe some of you might not know that. It's a Carbon Dioxide Information Analysis Center, which is a branch of the Department of Energy. And the proven reserves in the light blue are from EIA. And the reserve growth terms in yellow for oil and gas are from the EIA, and for the unconventional reserves, which are on the right, they're not really sourced in anything. They're just widely assumed to be very vast. So we just put a question mark there. And on the left is gigatons in terms of carbon content. On the right is their equivalent atmospheric CO2 concentration if it were all released immediately. Okay, so for the specific reserve estimate, historical emissions, just quickly, you can see that they add up to about 300 gigatons of carbon that were used up since the industrial era, and about half of that comes from coal, about 35% from oil, and the remainder, 15% from natural gas. And the conversion factors, since most of you are not used to thinking probably in terms of gigatons of carbon, but rather the standard units for each fossil fuel. When you see me saying 1 gigaton of carbon for oil, that means multiply it by about 8 to get billions of barrels. So basically, there's about 8 barrels of oil equals 1 ton of carbon. Same thing with natural gas. It's 60 trillion cubic feet of natural gas is equal to 1 gigaton. So multiply by 60 for natural gas to get the equivalent in trillion cubic feet. And about average for the different types of coal is just under 2 billion short tons for 1 gigaton of carbon. So a broad overview of our emission scenarios, general properties, all of them reflect global emissions for each fuel. So I'm not going to be talking about regional emissions or national emissions and so forth, but rather just the globally integrated emissions. One of our 5 scenarios is what we call a business as usual scenario. That is one that incorporates no mitigation policies, that is no restriction on the carbon emissions. And the remainder, the 4 are mitigation scenarios, all of which have coal emissions phased out by 2050. And I should stress that this is emissions of coal, not use of coal. We assume in these 4 mitigation scenarios 4 different peak oil emissions trajectories, and all but one of which was just taken from published sources, the EIA and also the NERING data. Gas emissions trajectory was assumed the same in each case. Okay, so this is what we get under these assumptions for both reserve estimates and growth rates. For our business as usual scenario, on the blue line at the top is the total CO2 emissions combined for each fuel. Liquid fuel oil, in other words, is the black line in the middle. The red curve, the highest one, is coal, and the green curve is natural gas. And again, these aren't predictive peaks. We're not saying that it will happen here, but under these assumptions of 2% annual growth, we just extrapolated the 2% annual growth rate in each fuel that's been observed for the past several decades until the Hubbert peak, in other words, the midpoint of the total resource base was reached, and then just assumed a 2% annual decline after that. So when we do that, we get a peak for natural gas at 2031, peak for oil at around 2016, and again, that's taken directly from a paper by John Wood. I think his name's John, but it's J. Wood et al. These are analysts from the EIA, which they did essentially the same. Well, they did exactly this, which is a 2% growth until the midpoint and 2% annual decline after that. For coal, the peak is all the way in 2077, and therefore the emissions peak is also right around there. Now, the total cumulative emissions over the 21st century are listed on the right, at the top right. It's about 1,100 gigatons of carbon total. Again, multiply by 8 to get billion barrels oil equivalent, or 2 to get billion short tons of coal. 700 of those were from coal, 240 were from oil, 130 were from natural gas. And it's become sort of a common metric to assess what is the reduction or the growth rate in the year 2050 of emissions compared to what they are now. And under our business as usual scenario, this is listed on the bottom left, the percent change in 2050 emissions, total emissions versus today's total emissions, is an increase of about 30%. Okay, so for our first mitigation scenario, which is our baseline scenario, which we just labeled coal phase out, we assumed, again, the same thing as far as the growth rate, 2% annual growth rate, until the peaks for oil and gas. And for coal, we imposed a peak in that we assumed 2% growth until 2012, and then we assumed that developed countries would phase out their growth rate, or they would level off their growth rate rather, until for the next 10 years, and then while developing countries were still allowed to increase their growth rate over that period. So until 2022, there's a global 1% annual increase in the growth rate of total emissions of coal, and then a linear phase out from thereafter until the year 2050. So that's again just the red curve is for coal. The dotted line, by the way, is the present. So left of that is historical. Right of that is projected. So the percent change there. Oh, by the way, the total emissions in this scenario, the first mitigation scenario, are just under half of what it was under our business as usual scenario, and about a third of that is coming from coal, about a half from oil, and another third from gas. And the percent change in 2050 in terms of the total emissions versus the present is a reduction of almost 60%. Now for our next mitigation scenario, we looked at the alternative peak oil trajectory from, again, from Wood et al. This is where they assumed, they extrapolated to 2% annual growth rate in oil use until a reserve to, they call it production, we just called it emissions. So until the reserve to emissions ratio reached a value of 10, I think it's about 50 at the moment, and then they kept the reserve to emission ratio fixed at 10 until oil was essentially depleted. And so that's the purple curve there. The red curve on the left is historical. Green is the 2016 peak, assuming symmetrical growth and decline rates. And the total resource base in both cases, oil resource base, was about 3 trillion barrels, or about 160 gigatons of carbon. Oh, no, sorry, that's, 300, about 200 something, 250 gigatons of carbon. I was thinking of the remaining reserves. In our, so in this scenario with the delayed peak, the peak in oil that lasts until the reserve to emission ratio gets to 10 and is fixed thereafter, the emissions projections are shown here. The total 21st century emissions go up by a total of about 20 gigatons because more oil is being used up before the 21st century is over. And the percent change in the year 2050 in terms of total emissions versus today is not that much different from the symmetrical peak in oil scenario, which I showed earlier. It's about 54% lower. Okay, so for our third mitigation scenario, which we call the less oil reserve scenario, we just removed the reserve growth term. So we set the reserve growth term equal to 0, but still assumed EIA's conventional reserve estimate for oil. And when we do that, our total resource base, the remaining oil resource base is only 160 gigatons of carbon, or about 1,300 billion barrels, as opposed to 250. So the 90 gigatons of carbon have been removed. And when we do that, we see that the percent change in emissions between 2050 and now is down by about almost 70%, and the total emissions are down by about 70 gigatons by 2100. Finally, in our fourth mitigation scenario, which we call the peak oil plateau scenario, we just took the oil emissions curve from Richard Naring's study, which I didn't have the raw data for, so I basically just picked the numbers off the curve. It was published in a news blurb in the journal Science. And I confirmed this with him, and just from inspection you can tell that the total resource base that he assumes there for this peak oil plateau occurring from 2020 to 2040 is significantly higher than the resource base assumed in the EIA projections, specifically about 400 billion barrels higher, so about 50 gigatons of carbon higher. And when we do that, the 21st century total emissions increase slightly to about 550 gigatons of carbon, and the percent change in 2050 versus 2007 versus the present in terms of total emissions rate is decreased by a slightly less amount, 40%. Okay, so how do these 5 mitigations, these emission scenarios, 4 of which are mitigation scenarios, compare with the SRES, the 6 illustrative or benchmark scenarios that I mentioned earlier. Well, our BAU, the business as usual scenario, in which there are no restraints on carbon emissions, is shown as the red dotted line. The blue dotted line is the coal phase out, assuming the delayed peak in oil to 2037, and the green dotted line is assuming the symmetric peak in oil at 2016. And you can see that our business as usual, well, first of all, the solid lines are the SRES, the IPCC emission scenarios, which, by the way, are by design don't incorporate any mitigation policies. In fact, mitigation is left for a whole separate report of the IPCC and a whole separate working group. And that's, in case you ever want to look it up, it's called Working Group 3, and the report is just titled Mitigation of Climate Change. So their mitigation scenarios are left for that report, but these are just emission scenarios that don't incorporate climate-related policy changes, but might incorporate other policy changes that happen to be to result in a decline in emissions, namely, the transition to renewables and so forth. So what we see here in general is that our business as usual scenario, the red dotted line, is much lower than the SRES business as usual scenarios, the 3 solid lines at the top. The A2 scenario, which I think is what Randy was showing the temperature consequences of in his animation. That assumes, that's pretty extreme, clearly. It's about 1,800 gigatons by the end of the century. So almost twice as high as our business as usual scenario in terms of cumulative emissions, and almost over 3 times higher than our standard coal phase-out scenario, where coal emissions are phased out by 2050. Okay, and also our coal phase-outs and our mitigation scenarios are much lower than the lowest IPCC emission scenarios, B1 and A1T, the purple line shown at the bottom. All right, so to convert these emission scenarios into CO2 concentration time series projections, so we just incorporated what's called a pulse response function. This is a parameterization of a well-tested, well-documented carbon cycle model, the Bern model. And the equation shown there, obviously I'm not going to go through the whole equation, but basically what this function shows is that if you emit a certain amount of CO2 into the atmosphere, how much of it remains in the air after a given number of years. So that's what this trajectory shows. And so what this parameterization of this carbon cycle model shows is that, first of all, about half of it is gone, half of any emission is absorbed by the land and the ocean, what we call the sinks for atmospheric CO2 in about 2 decades. But then it's very slow after that, effectively meaning that a significant fraction of it, almost a fifth of any given CO2 emission, remains in the atmosphere for an eternity, for all practical purposes. Okay, so when we use this pulse response function, convolve that with our CO2 emissions trajectories, first of all, as is standard in these types of studies, we compared the historical emissions data, plugged that into our little calculation, and then compared those to the observed time series of historical atmospheric CO2. And we see here that there's a discrepancy, but we'd expect that because we've only looked at fossil fuel CO2 emissions, and we know for a fact that a significant portion, about at any given time in any given year, it's about 1/5 to about a third of total emissions of CO2 from human activities is from land use changes and deforestation. But there's much greater uncertainty in that than there is in, well, I should say there's probably as much uncertainty in that as there is in what we've been talking about here, namely the fossil fuel reserve estimates. So there's really no point in trying to incorporate those into our model. Rather, we looked at the average difference between our projected CO2 and the observed CO2 over the historical period. And we find that on average it's about 15 ppm difference. So we simply propagated that difference through our projections as well. And also as a result of this analysis here, what we see is that total, at least according to this model, total fossil fuel CO2 added to date is just over 80 ppm. Remember, that's about of the roughly 100 ppm that have been added since the pre-industrial era. And that also shows, by the way, I should go back to this and explain something else very briefly. This shows that the question that sometimes comes up, I've been asked, in your emission scenarios compared to the CO2 time series projections, why don't the maxima in the emissions match the maximum, the peaks in the CO2 concentrations? Well, that's simply, first of all, that's what we'd expect in nature, because there's only two cases when that wouldn't happen. One is where the response by the system, in other words, the CO2 sinks that I mentioned, the uptake by the land and the ocean are instantaneous, which is not the case, or the emissions cut off immediately after the peak emissions year. Those are the only two cases, assuming the model's working properly, those are the only two cases that, that we'd expect the maximum in emissions rate to match the maximum in CO2 concentration. So the point is there's this long residual effect of any emitted CO2. Okay, so as far as our actual projections of atmospheric CO2 concentration for under our business as usual scenario, no constraints on emissions, the total emissions or the total CO2 concentration at the end of the century is about 300 parts per million higher than the pre-industrial level of 280 ppm. In other words, well over doubled CO2, which if you look at, I won't go into the details, but the change in the planetary energy imbalance implied from that would be around 2.5 watts per square meter. And as a result of that, the warming cap that I mentioned before of about 1 degree Celsius lower than the current temperature is extremely infeasible. It would be to achieve that, if not impossible, due to the CO2 increase alone. And this implies, of course, that this pretty much constitutes dangerous anthropogenic interference with the climate system, because after this, the feedbacks that are expected from the temperature increase might spiral out of our control. And sorry, that's another thing I didn't mention about this, the pulse response function. One drawback of this is that it doesn't represent these temperature-related feedbacks. In other words, as you heat up the air and the ocean, for various physical reasons, you'd expect more CO2 to be released from both the land and the ocean. And those aren't represented here. So really, our CO2 projections should be considered lower limits, or underestimates, in other words. Okay, so, and the higher the CO2 level, the more feedbacks we'd expect. So for our first mitigation scenario, our baseline coal phase-out scenario, where oil peaks in the year 2016, we find that the maximum CO2 level is in the year 2050 at about 440 ppm, which is under, remember, our cap of 450 ppm, and by, for 50 years after that, it declines because the CO2 emissions decline by about 10 ppm to 430 ppm by 2150. And the change in planetary energy imbalance is relatively modest, just under 1 watt per square meter, which means that warming under 1 degree Celsius above the present would be achievable under this scenario. And same thing goes basically for our coal phase-out scenario, in which we have the delayed peak, the peak at oil peak at 2037, although the CO2, the peak CO2 concentration in 2050 is about 460 ppm, which is about 20 ppm higher than this scenario. It's still, the difference declines over time simply because the emissions decline more quickly over time. And so the 2150 concentration is basically the same as in the earlier oil peak scenario. Okay, so for our less oil reserve scenario, remember that's the scenario in which there's zero reserve growth in conventional oil. We find a slightly lower peak in the atmospheric CO2 in the 21st century of 430 ppm, and that implies an even lower change in the planetary radiation balance, and that means warming under 1 degree Celsius should be slightly more achievable under that. And the same thing here. I won't go into it much in detail. This is using the peak oil plateau of narrowing it all from 2020 to 2040. The peak CO2 concentration is about 10 ppm higher than our baseline mitigation scenario. And so this is just a quick summary of our results. I won't go into every single one of them, except for that first yellow row there. That's where we considered, well, I'll talk about both yellow rows. The first one is where we considered IPCC and World Energy Council estimates for conventional oil and gas, which are significantly lower, up to I think about 20 or 30% lower for each fuel than the EIA estimates. And what we find is that the peak CO2 level, when I ran that, it's about 20 ppm lower than the peak CO2 level in our coal phase-out scenario, the baseline mitigation scenario, and the peak in CO2 happens slightly earlier by about 2040. And for coal, if we shift coal phase-out, if we realize, which many people, including Jim Hansen and many other climate scientists, are beginning to think that the dangerous level of CO2 might well be even below 450 ppm. And in fact, we might already be at what's considered a dangerous level of CO2 at 380 ppm. As I mentioned, we seem to have already passed at least one tipping point in the climate system, namely for the Arctic sea ice. And also there's disturbing trends, or at least we don't have quite enough data to call them trends yet, but disturbing increases in the rates of melt coming off of Greenland and West Antarctica. And so that could mean very undesirable sea level rises that quickly spiral out of our control, because these are positive feedbacks, that is, feedbacks that responses from the natural part of the climate system that amplify the imposed warming by humans. Okay, so broad conclusions and implications. Business as usual scenario, even though ours is much lower than the SRES scenarios, it still implies double pre-industrial CO2, which means at least a 2 degrees Celsius increase by the end of the century, which again, remember from the paleoclimate data, last time it was 2 to 3 degrees warmer than it is today. Sea level was on average 25 meters or 80 feet higher than it is today. And also, the higher you go in terms of atmospheric CO2, the more likely you are to encounter the climate-related feedbacks that I mentioned. On the other hand, our coal phase-out in general, of the type that we've described, where you have what I'd call massive phase-out over a period of several decades, if that happens by mid-century, total global phase-out of coal emissions, not necessarily coal use, but just coal emissions, for example, by things like carbon capture and sequestration, then that would have numerous benefits, including minimizing the climate-related feedbacks and, most importantly, keeping the global temperature below 1 degree Celsius, and also as a side effect, nice side effect, cleaner air, because there's less particulate combustion byproducts from the fossil fuels. So the conclusion there is, of course, that sequestering coal emissions really must be a top priority for climate change mitigation globally. So in terms of peak oil, with all the uncertainty that there is in oil estimates and peak oil timing and so forth, what we can glean as a sort of general concept is that an earlier peak would be, if there is such a thing, better than a delayed peak, in which we delay the peak until we get to some fixed reserve to production and reserve to emissions ratio. And that could reduce CO2 by a fairly significant amount, about 15 parts per million, which again, when you're talking about a threshold for dangerous interference with climate, every ppm might end up counting. And also from this, if we don't wait until the reserve to emissions ratio gets that low, the decline rate won't plummet as the oil peak in 2037 emissions plot shows, and therefore less economic disruptions and so forth. And also maybe we'd be less tempted to turn to unconventional fuels. That is, if we stretch out the conventional oil supplies that we do have, there might be this lower temptation out of desperation to resort to the unconventionals, which again are widely assumed to be vast and therefore pose a serious threat in terms of controlling climate change. On that subject, large-scale use of unconventional resources. Remember, we didn't even factor in unconventional resources because of our imposed cap on CO2 level. Without sequestration, it almost guarantees dangerous climate change, with large-scale disintegration of ice sheets and so forth, species extinction, all the things I mentioned. So the broad policy recommendations in terms of coal emissions, global coal emissions phase-out really must be enacted soon. And this, in our opinion, it seems likely that the only way to achieve this would be in some legally binding international treaty, much like the Montreal Protocol, for instance, for ozone-destroying chemicals, which had a very significant effect very shortly after it was ratified. And thankfully, our government also ratified that. But what we see now is a significant decline in the emissions rate of ozone-destroying chemicals. We still don't see a full recovery or even a significant recovery of the Antarctic ozone hole, which, by the way, if you see people being skeptical of climate change because they say, well, Antarctica is getting cooler, well, that's also anthropogenic interference because we've destroyed the ozone hole, the ozone layer above Antarctica. So it's because of anthropogenic interference that Antarctica isn't as warm as it's projected to be. So the other near-term focus, and I really like what Congressman Bartlett's energy advisor said earlier today, the near-term focus should really be on very simple, very achievable using current technology, energy conservation and energy efficiency measures. And after I was talking with him earlier today after he talked, and he said that I should reverse the order and say conservation should come first, energy conservation measures. And then we can use some of the conserved energy to go into energy efficiency measures. Whatever, as long as it achieves this goal of stretching out conventional reserves so that we don't have as many economic disruptions and we don't, out of desperation, resort to unconventional fuels. Yeah.
I have a question. How would the findings change if you included the climate change feedbacks, especially the methane positive feedback?
Oh yeah. What do you mean? You mean the? He asked how would our scenarios change, our projections change if we did incorporate the climate-related feedbacks, especially the methane feedback. By methane feedback, do you mean what's being observed over Arctic permafrost, for instance? Yeah, so first of all, that's not a huge flux, although it is detectable, of course. But yeah, that is already one example of another example in the Arctic of why we might be past a tipping point for at least some components of the climate system. The Arctic permafrost degradation, which is the source of the methane that you're talking about, that's not necessarily irreversible. In other words, those feedbacks don't have the potential necessarily to spiral out of control if we control emissions and therefore control further CO2 and methane increase in the atmosphere. If we don't, then all bets are off, and that's why we didn't even bother to incorporate unconventional fuel estimates aside from the uncertainty with regards to their magnitudes. Yeah, if we did, we'd certainly go way above pre-industrial. Conservative in terms of CO2 concentration, yeah, but I bet a lot of people here would say liberal in terms of the reserve estimates that we use. So optimistic in terms of energy reserve estimates, but yeah, conservative in terms of maximums in CO2 and atmospheric CO2 projections. So another policy option, a broad option, is just viable alternative energy sources. Obviously, these are really common sense, of course. That's why I mentioned that even though this is unpublished work, we're very optimistic that it'll be published, by the way, in more or less its current form in a peer-reviewed scientific journal. But our conclusions are fairly robust and, like I said, basically common sense type things. But alternative energy sources, I personally am slightly skeptical about some of them. But what I really would like to see and what I think must be done in these things is a full pipeline energy and carbon accounting. So as a corollary to that, we could develop what are called carbon neutral or even carbon negative biofuels and renewables. And a big question mark, possibly also further development of nuclear, although, I mean, I'm just as leery as anyone else about that. If we really decide that to get serious and we start realizing more and more quickly that we're approaching a very dangerous level of atmospheric concentrations of greenhouse gases, then we might have no other choice but to really quickly wean ourselves off of fossil fuels. And on the biofuels note, I should mention that's obviously a much maligned and much debated subject, rightfully so. But the way it's being done now, anyway, in terms of food crops being used for biofuels, I mean what's that? Now that, in my view, would be a disaster because, first of all, we're already seeing, so let's take the palm oil plantations in Southeast Asia. We're seeing palm oil is also used for food, of course, but a good chunk of it is used for biofuel. And that's coming at the expense of tropical rainforests. And you don't have to be a tree hugger to realize that that's extremely undesirable from multiple perspectives, ecological and climatic, in terms of carbon loss, the stored carbon that's in the forest being lost. So yeah, if biofuels are done properly, then they might well be carbon negative. In fact, there was a paper which we cite in our paper here by Tillman et al., a group from University of Minnesota, in the journal Science last year, that looked at what they consider to be carbon negative biofuels, but not at all what's traditionally thought of as biofuels. The title of the paper was Low Input, High Diversity Grasslands as Potential Biofuel Sources. And I won't go into all the details. I can send the PDF if anyone's interested, but basically they found that if you apply their techniques, which are mainly for use on degraded or abandoned agricultural lands, simply by seeding them with native prairie grasses and such, then if you extrapolate the global area, and actually they use pretty conservative estimates for the global area of the land surface covered by degraded or abandoned agricultural lands, they found that conservatively you could, conservatively you might be able to supply between 13 to 19% of the global energy demand for both transportation and electricity. So if there is potential in biofuels, in my opinion, if they're done properly. Okay, so that's really all I have to say. In closing, just acknowledge the following data and funding sources. And in terms of this conference, thanks to the people that I interacted with, the two Sallys, Randy and Steve Andrews, for getting me here. And if anyone has any questions, if you want any copies of the paper or any questions in general about climate change, feel free to shoot me an email. I'd be glad to talk to anyone. Okay, well, thanks for your attention.